So yeah, I'm David Airlie. You may know me from previous LCAs. I've pretty much given similar talks. I work at Red Hat in Brisbane. I've been there quite a while now. Unlike Keith, I'm not giving up graphics tomorrow, or last week. I've moved. But my talk today is about a technology that sort of caught me by surprise last year, sort of like mid last year, called DisplayPort MST, which stands for multi-stream transport. And it's pretty much involved in a whole lot of devices that when I initially saw this idea, I went, oh, you'd never use it for that, but well, everyone did. So the two main things that this technology affects are 4K screens and lots of later laptop docks. How I actually started working on this was quite accidental. One of the local, I work in the Red Hat office in Brisbane, but most of my management and all that is done through the US. But the local IT guy in the office walked in one day in my cubicle. I was like, oh, someone from around here. And he goes, how come this laptop doesn't work with two monitors when I dock it? I don't know. Well, could you have a look? So I said, oh, I'll have a quick look at this. It can't be that hard a problem. Silly. So he went, because they had actually bought some of these laptops, some of the docks, and tested it with one monitor plugged into the dock and went, well, it's fine, we'll give it to users. And then someone plugged in two monitors into the dock and it just mirrored. And they was like, why isn't this giving us two monitors? We've already given it to people. Please fix. So I went and dug into it a little bit, figured out what was going on, and realized, I came back to myself, it's probably going to take about 6 months maybe. And he was like, what? We got to get these out to people now. I was like, yeah, you pretty much have to implement a whole networking stack to get this working. I was like, okay. So I said, well, I'll start doing it now. I told my boss like a couple of days later that I was actually starting on this project with it, and it would probably take the next 6 months and ruin all the other projects I was meant to be working on. But since it seemed important that we should have this stuff working, Red Hat has customers apparently. Who knew? So yeah, and keeping them happy is more important than doing my other projects that I like.
No Virgil for us.
No, Virgil, hence why the Virgil talk is not being given this year. Just a quick intro to the area, history of like display technologies. I'm not going too far back. I'm not talking, like, I'll start at VGA. No need to keep going further back, but VGA was like probably the most sort of successful of the display technologies that's been around. It was like analog based. It did everything for analog monitors. People were quite happy with it for many years. But things have to go digital. There's no point having an analog signal in your loop when everything is digital on either end, especially with flat panels. So along came DVI. DVI started out as those 4 little pins in the cross are actually a VGA port, and the rest has some pins of the VGA port and a whole set of digital channels. So it was like an evolution of VGA. You could get DVI that was just digital. You could get DVI that had digital and analog transports, and you could get DVI that was just analog, which was actually VGA. But I don't think anyone ever shipped that in a product. There was a standard, it just wasn't in the products. DVI was good also. It had sort of extra pins, so they put 2 digital channels into DVI. The second digital channel started being used for a thing called dual-link DVI, which was only certain graphics cards would support this, and it was for big monitors. At the time, big monitors usually meant Apple 30-inch, Dell 30 inches, that sort of monitors used dual-link DVI. 2560 by X, big numbers. For the time, not big numbers now. But DVI sort of got remodeled and put in a different shaped connector with only one link in it called HDMI, and that was done by a different consortium of people because it's the computer industry is not the same as the entertainment industry, and everyone likes their own standard and everyone likes to charge money for different things. So HDMI came along. HDMI is one of those things where you have to pay the HDMI people for using their connector. Their cables cost $70,000 million if you buy them with gold plating on either end, even though they're the same cables that cost $5. But it was a good scam, and people are still running with it. It's a good call. And around the same time as HDMI, DisplayPort started coming out, probably a bit later, but not too much different. But DisplayPort was the sort of computer industry attempt to come up with a new standard. They went a lot further. HDMI is pretty much DVI with a different plug and then adding features to it and making it, more stuff for TVs and stuff. DisplayPort was like, throw everything out the window, and we'll pretty much start again with a cool socket, cool plug. And so here's a nice picture of what the sort of way DisplayPort looks. You've got a receiver and transmitter. Between them, you've got a big, large link, main link. You've got an Oxy H channel and a hot plug interrupt. The main link consists of up to four channels, and the four channels can have different data rates on them depending on how much you need. So the original DisplayLink data rate was 162 megabits a second, along with 270 megabits a second. So each channel could do that, and then you could have four channels. So that was quite a good bit of bandwidth. The DisplayPort 1.2 spec has upped that to 540 megabits, which is called 1.2 high bit rate. And there's another one coming in DisplayPort 1.3, which I'll mention later on. But the idea was, depending on what you plugged in, you didn't need to bring up all the channels. It's kind of like sort of like PCI Express, similar, like you have a number of lanes and you don't want to use all the lanes. So this was the same thing. You'd have, some monitors would only need one channel, some monitors would only need one channel at the low bit rate, some might need two channels at the low bit rate. There was also some silly things the spec didn't quite say, like, well, if a monitor could do it with either two lanes at the low rate or one lane at the high rate, which one should I pick? And it seemed like some people picked one and some people picked the other. So there was actually some little incompatibilities even after they'd specified all of this. But the main link pretty much transports all the data. It's got like the video data in it, it's got audio data in it, and a few other little things at the time but mainly it's just video and audio in it. Oxy H is a control channel, so it's just your standard way of signaling between the two devices to set everything up before the data starts flowing. I'll talk a bit more about what goes in there. And then there's just a hot plug interrupt, so the receiver can ping the transmitter and say, wake up, I need you to talk to me, and the transmitter will send it a request. The Oxy H channel is 1 megabit per second in DisplayPort 1.1, but in DisplayPort 1.2 they added a new thing called fast Oxy H. Again, I'm not even sure hardware supports this, it's optional in the spec, but it can go at 675 megabytes a second, sorry. The reason that is they're actually using that mode to put USB over it, because why wouldn't you? I'll get to something even stranger. Actually, I probably haven't got a slide, but I'll mention something stranger later. So yeah, the idea was that you can stick USB over this fast Oxy H channel, and your life will be much happier because you'll have one cable to your monitor, and all your USB will go over it, and all your display, and all your audio. So that was the original DisplayPort. That mode was called, DisplayPort 1.1 is called the single stream transport. There's only really one stream going across it. It's going from your transmitter to your receiver, and there's one of each. The things that came out on that, you'd either have a direct DisplayPort to DisplayPort connection, you could have a DisplayPort with a converter on the end. The converters would do then DisplayPort to VGA, DisplayPort to HDMI, whatever you wanted. You also had two classes of converter. There's a standard part of the standard called DisplayPort Plus, I think, which some of the pins could swap into DVI HDMI compatibility mode. So you get a converter that just was very simple, and it would just make it pump HDMI or DVI out. But it could only do single link. So if you had a dual link monitor, you had to get an active converter, and there was a bit of confusion around that area as well, whether active converters and passive converters, and some of the active converters needed power and some of them didn't, and kind of messy. The spec also specified a bunch of random things I don't think I've ever actually seen, like repeaters, replicators, and switches. I've probably never actually seen them in the real world, but they were all specified by the spec. So this Oxy H channel is where most of the control channel, a lot of the fun things are done. This is pretty much, it's like a register space in the receiver that the transmitter can request read-write out of. So there's a native Oxy H transport, and you basically have a register space that's, I think it's about 64K now, and you give it an offset and write a bunch of registers, you give it an offset and read a bunch of registers. It also has a secondary I2C transport on top of it. So for compatibility with old monitors that needed like EDID, well, not old, all monitors still use it, but EDID, DDC, CI, all of these other interfaces that run over I2C, instead of trying to redo those all with Oxy H, they just made an I2C sort of emulation on top of the Oxy H channel. And all in all, that sort of worked out pretty well. We had a handle on all of this last year, and it was all going really well. But then along came multi-stream transport. So what is the multi-stream transport? They pretty much decided one transmitter, multiple receivers. They take that transport link that we had, that link that we've got, split it up into a number of individual blocks. So there's 63 blocks on the link. You can assign those 63 blocks into different virtual channels, and then you can point those virtual channels to some receiver block. So the idea was, well, we've got this large bandwidth link. I want to be able to run 2, 3, 4, X number of monitors and things off the other end of it. How this is implemented, I'll get a little bit into it, but I'll get a bit technical after this slide for a couple of slides, just to show you how awesome I am, but otherwise it's not too bad. But it's mainly they've sort of layered a whole messaging system on top of a bunch of the DPCD register space. So the DisplayPort register space has, I think they're 48 byte buffers or something really silly, that you write messages to go up and get replies back, and then messages to go down and get replied back. So there's 4 of these buffers, and you can send these types of messages up and down the tree. And you can send broadcast messages and a number of other things. Here's an example picture from the spec, which I've nicely cleaned up and put into a nicer picture. I hope you can read the line down the bottom. You probably can't, it's behind the things, but I'll say it out anyway. But the idea, if you look at this picture, is you've got 2 source devices, you've got 5 branch devices, you've got like 5 sinks sitting all off them. The numbers they're called the port numbers. So the source 1 looks out at the 0 port, it sees branch 2. So the thing at the end is say if sink 1 relative to source 2. So if source 2 wants to send a message to sink 1, it looks at its 0 port, then branch 1's second port, then branch 2's second port, then branch 3's first port. And that's how it sends a sideband over the aux-CH. It starts it at the top and gives it an address. So every device in the tree has a GUID, a global identifier. It's 128 bits, 128-bit number. Nearly every device I've gotten, I've had to program that into it at the start. When it connects, they generally don't have anything in them. The spec says the only time it needs to be initialized is if you have a device that is both a DisplayPort device and a USB device. Some property of the USB device needs to show the GUID the same as some property of the DisplayPort device, so you can match them up. Otherwise, the OS has to assign random GUIDs to all the devices. The main use for the GUID is to avoid loops. You can actually plug these things back into each other, and the whole idea is that you should detect that and not try and send messages the wrong way or have messages going around in circles. Each of these devices at the bottom, you can probably just see a 0.2.2.1 line. That's called a relative address. So you want to send a message to someone, you need to know his relative address. You stick stuff into a buffer with that address and the packet on it, and off it goes to the guy, whoever wants to sit at the end, one of the sinks. I have not built something that looks like this. I don't have enough devices. In fact, I think I've only got like source 1 and maybe 2 other levels, and even then that was quite hard and messy to get working. In terms of payload and bandwidth management, you have to manage the bandwidth. As I said, it's cut into 63 slots. You can have up to 63 virtual channels. Probably not so useful to have 63 of them, but that's how many you get. The way it works is they have a number called the payload bandwidth number. If you take the number, for one lane at 162, we get a bandwidth number of 3. These are like just for 4 lanes at 540, you've got a bandwidth number of 40. So the idea is every one of those 63 slots, at this rate, you would need 3 PBN. So you got 3 by 63 at 1162. At 4, 540, you got 40 by 63. So as an example, this mode, a 1920 mode by 1200 mode at 60 hertz with 30 bits per pixel, this is the example given in the spec, requires 689 PBNs. So you got to say, well, that's not going to work at one lane at 162. And so how many, I should have divided it out on the screen, but yeah, divide 689 by 40 in your head and you'll get the idea of how many of the 63 slots you're going to need. And that assigns for that monitor. And the next monitor, you need to do another chunk of slots. And this worked really well if you hadn't got big monitors. But I will get to why this is a problem later. But that's sort of the basics of what MST is. It's like a layer over DisplayPort that cuts up the DisplayPort transport into 63 bits and lets you address individual devices on the end of it. Again, those slots can be used mostly for video, but there's also audio sideband stuff that you can stick over to do the audio transport. USB still goes over aux-CH. Just to give you a quick example of what the protocol looks like, I won't go into too much details on these. Are not that interesting unless, I'd say I'm the only person outside of DisplayPort that has read them, and whoever reviewed the patches. But link address. So yeah, there's an address discovery. So you're a source, something gets plugged in, you get a hot plugged interrupt. You got to go find out who's there. So link address pretty much is you send it out and wait for all the answers to come back, and you find out how many things are in the tree. Connection status notify and resource status notify. They're things you receive from back up the tree to say something's changed. So if further down the topology, somebody unplugs a hub or a monitor gets turned off, you'll get a connection status notified to say something's changed, reconfigure things to suit that change. Resource status notify is if the bandwidth something changes. So maybe something, I actually don't really know when this is going to be, maybe a hub gets something else plugged in or it goes into a lower mode or something. In that case, you get a resource status notify saying, I used to have this much bandwidth, I've only got this much now, or I used to have a small amount, I have more now. It lets it dynamically change. Enum path resources is a way that you go, okay, I want to get a connection from my source to that sink. How many PBNs can I get? So what bandwidth exists in the system right now for me to put on that, just to check that when I get a mode, if I need 600 PBNs and there's only 400 on that link, I can't give that mode to the user. So it just allows you to block cases that you know you can't fit into. Allocate payload is, okay, I think there's enough bandwidth, reserve that bandwidth for my channel. And clear payload ID table is when, something's happened bad, everything reset, just nuke the tables. So they're pretty much the data setup and the discovery stuff. There's not a huge amount of messaging. The sideband message protocol is kind of messy. There's like 2 different CRCs involved in it. You got to split the messages up into small chunks, and some of the messages are quite long. The spec is kind of badly written. It's hard to sometimes interpret whether it should be big endian or little endian, exactly where things go. And because I was writing this against hardware I had not really much knowledge of and I had no examples for, it took me quite a while of just sticking numbers in and hoping something came back. Eventually something did, though. I think it was about 2 months, but about that time. The MST, these are more like, so you've got device down the tree that's a DisplayPort device and you want to talk to it just like it was locally. So you can ask it to remote DPCD, so you can look at its registers. Remote DPCD read and write, I don't tend to use them. I don't think I've actually had to use them at all so far in the way I've written this. Remote I2C read and remote I2C write, you want those because you want to be able to get the things like the EDID, display ID, all these things that happen over legacy I2C buses. So they're quite useful things to have. Use them a lot. And then we've got power control, so you can say turn yourself off, turn yourself on, because you can do that locally with the aux-CH channel as well. So that sort of like covers the bones of the spec. The spec is not a public spec either, which is a bit of a problem. You have to be a member of Visa. I'll say no more about my membership status because I'll probably get in trouble. But I have a copy of the spec, and I implemented it from the copy. I had a copy of a draft copy of the spec. Lucky somebody gave me the real one because the draft had quite substantial differences in a number of areas, which confused me for a while. But that's the sort of basics of it. There's a bunch of code in the Linux kernel. It's not actually a huge amount of code yet, but there's a bunch of code in the kernel. If you want interested in it, join Visa. No, don't. Actually, just talk to me or talk to anyone else. It's definitely it was an interesting project to sort of take on from scratch. I had no idea about it before the guy dropped the stuff on my desk, and it was quite interesting. But so that was the protocol. But why is this being used? What was it for? I originally heard of this spec, the idea behind this a few years ago. I'd say about 2 or 3 years ago. When DisplayPort first came out, there was a promise of daisy chaining. That was all we ever really heard about. There was, you could plug a monitor into your computer and plug another monitor into the monitor, and it would make things easier. And we had some customers who were like, we've got like 3 monitors on our desk and we'd rather not have to run 3 cables down around and underneath things. Can we do it at 1? And that was the only sort of promise I'd really heard about it. I hadn't really thought about how is this going to be used. So that's why I was so surprised when this turned up in laptop docks, because why? It just seems like, why does this make sense in laptop docks? It seems like a lot overkill, and to be honest, I still think it's overkill. But hardware, wires. Basically all it does is it reduces the number of wires going from the dock, from the laptop to the dock, from If you've got a VGA port and a HDMI port on your dock, or VGA, DVI, whatever combinations, they all require their own channels and wires. This allows them to run, essentially, I'd say, a DisplayPort set of wires. So like 6 wires through, and then they've got a smart device in the dock, and then that smart device, actually, calling it smart is probably not a great idea. They have a device that claims to be smart in the dock. Those things are, again, it's written by firmware, guys. So that explains the level of how smart it can be. It locks up a lot. And the only solution is to power everything off. Guess how much fun that was. So, but laptop dock manufacturers love this because it saves them wires. And that makes them happy. So it showed up in pretty much everyone's, I think, all the Lenovo's, all the Dells. I've seen it in like 3 or 4 places now, all the docks are using it. And it kind of makes sense now. You go, okay, well, you've got the DisplayPort plugs in your dock, and you've got your VGA and DVI, and they're all just one DisplayPort, and then from the laptop's point of view, it's much simpler, and the dock just has a little bit more smarts in it. So that was interesting, and I've sort of accepted that's the way things are going to be from now on. Another area was called, these things called MST hubs. Again, I heard about these about 3 years ago, but we've never been able to buy one. We've been like, can I get an MST hub? Oh, people would announce them. Like AMD were big into trying to ship these a few years ago, and you just couldn't get them. But the idea behind these was, if anyone's seen like AMD's Eyefinity, putting 6 monitors onto one graphics card solution, where they end up with 6 mini DisplayPort sockets on the back of a card. It gets a bit cramped on the back of the card. Well, the idea that AMD had was, we'll just put 1 or 2 mini DisplayPort sockets on the back of the card, and you can buy 2 of these little hubs, and the little hubs will then break out to 3 DisplayPort adapters, and you can plug in your 6 monitors into one card that way. It was a good idea, but again, these took so long to come to market. Eventually, when I started looking at the docks, I went, oh, well, I may as well try and buy these. And I actually managed to buy 2 different ones. One of them is a later model that seems to be semi-acceptable. The other is actually, it seems to be an older model because they've used 2 hubs. One, to get 3 ports, they got 2 2-port hubs and just sort of cascaded them. So it's like, yeah, we obviously got the quick-to-market design, but really crap. But again, you see these all over the place. No, you don't see them all over. I've got 2, so yeah. I'm sure no one else in this room has ever seen one. But maybe someday you will. And they might work. But yeah, they were mainly an AMD type thing. They're not really much, NVIDIA are probably useful on as well in a way, but AMD are doing it with 6 scan-outs, so they're crazy. Not much use. So the other place these also showed up in was 4K monitors. Now, this also took me by surprise because, well, yeah, monitors, they're just a monitor, but the problem that people were facing trying to get 4K monitors to market quicker than everyone else and get them in at a specific price was there's a piece of hardware in the monitor that they couldn't get fast enough. No? What was the reason?
Intel chips.
Oh.
Go fast enough.
Well, that was one reason, yes. One reason. Okay, I'll give that reason the next time. But they basically, yeah, there's 2, I'll give it in a second. There's 2 in the monitor. So they end up there wasn't enough bandwidth to sort of like draw a full monitor off one clock, off one scan out from the chip. They decided, well, we'll just use 2. So what they did was they split the monitor into 2 logical, I suppose, panels, one on the left-hand side of the monitor and one on the right-hand side of the monitor. And each of these are 1920 by 2160 high, and then you add them together and you get 4K, and you're happy. So, well, the other reason that Keith has just given, and I'll actually say it a little later on, is the bandwidth requirement for doing one monitor is over the clock limit for a number of Intel graphics chips, and that would mean that you couldn't use these 4K monitors with a lot of hardware that people want to use them with, so it made sense to try and just split it. So they're the 2 sort of reasons. The hardware has caught up, you can get 4K. So there's 2 types of 4K monitor on the market at the moment, and this is why it gets annoying, and that's why 4K is going to be a bit of a pain to support. And there's single stream 4K monitors. You get those from Acer and Samsung, I think, are the 2 ones I've seen. The Samsung, like, is a 27-inch 4K monitor. I got one they plugged it into my laptop and it didn't work, and then I plugged it into the laptop that I thought was identical, but was a model up from that, and it worked fine. So it's like, oh, clock limits, you can't run this monitor on any laptop that's not heavy, was essentially it was like, Pick up a brick, it works. Pick up a laptop you actually want to use, it doesn't work. And some guy in my office had bought one of these to use with his laptop, but he had like an X240 or a T, and he was like, yeah, it's never going to work, just go back to your old monitor. And you can get the multi-stream versions. The multi-streams are the double panel ones. They come from, I think Dell were first, and I'm sure someone else is doing the same thing. I've just got Dell's because Dell gave me some for 2 months in May, and it's still on my desk. So they haven't asked for it back. And if they're watching this, I'm keeping it for a little while longer. But so how does this work in terms of DisplayPort MST? When you plug one of these in, you end up getting a hub with 2 ports with 2 connected devices on it. There's a concept in MST of physical and logical ports. So laptop docks would have physical ports, hubs have physical ports. These have 2 logical ports. There's no real difference from the point of view of the kernel, but it's information you get the port start at a higher number. So you get 2 of these ports, and they both report EDIDs, and they both report EDIDs of 1920 by 2160 as their preferred mode. And then when you plug that into your standard Linux box, generally what happens is it comes up with 2 monitors with like a line, not only line, but it also gets them the wrong way around out of the box nearly always. So it's quite frustrating. But what happened at the same time was I plugged it into a Windows box, and it did the same thing. So I was like, well, some of these Windows drivers suck. So they obviously hadn't caught up either. So it was like, at least, I'm doing just as crappy as Windows is a good starting line. So what was required to make this better? And it's still an ongoing process. The idea was it's called monitor tiling. There's a protocol called DisplayID v1.3. Again, this is not part of the DisplayPort spec, so someone had to lend me a copy of this as well. It's a separate spec that, again, consortiums, makes no sense. It's a replacement for EDID that I think AMD may have started a few years ago, and the idea was, instead of just making EDID, enhancing it, let's just write a whole new display protocol and stick it on a different I2C address and make monitor manufacturers put it in. And I wrote the spec and I started writing, and then I started probing the I2C and going, no, there's nothing on this address on the I2C. What's going on? This display, it says it needs DisplayID v1.3. And then I realized somebody actually went, after a while, oh, nobody's going to do this. Like, the computer industry is insane, but it's not that insane that they're going to replace this protocol that we already use. So what they actually ended up doing was, we won't use all of DisplayID, but down in appendix like B or C, there's like a tiling specified extension. And it's a DisplayID extension. So what they did was they took the DisplayID extension, wrapped it in an EDID extension, and stuck it on the end of the EDID. So it's hidden away down the end in an extension block. So it's like, why? But don't ask. It's like, yeah, there's a special EDID extension byte called DisplayID, and then you have to open that up and parse the DisplayID protocol inside that, and then you get the tiling information out. The tiling information is, I am tile 0, it's an X and Y value of where you are in the full setup, how many monitors or how many tiles are in the setup, what size your tile is, and some information about bezels and stuff for those sort of cases where you have a big 6 monitors with big bezels between them and you want to specify that sort of thing. I currently ignore a lot of the sort of corner cases of this because it's painful, and I have no bezels, and no one's given me a monitor with bezels. So if someone wants bezel support, they know where to find me. But this is protocol. It wasn't that hard once I figured out where it was and what to do with it. But I've implemented most, and I think I've just merged some of that into the kernel. But that's the basics of the protocol. Just to go on to where are we from, like, how does DisplayPort MST work with hardware side? So you got your standard. I'm pretty much x86 only. I'm not really sure what's happening on ARM. I don't think anyone supports it on ARM yet. Intel have MST, DisplayPort MST support from Haswell onwards, and it was all the Haswell laptops with the docks that were the first one to do this and cause all the pain. Intel make these market differentiation things, and they've got 3 streams of Haswell. There's like ULX, ULT, and normal. So ULX can't do the high bit rate DisplayPort rate, but it can do MST. ULT I think can do the high bit rate, but can't sustain the clock over it. You can't use all of it just for one image. You can split it up amongst things. And then the normal one can do everything. So I've got a Lenovo T440S, which is a ULT machine. And I have a Lenovo T540P on my desk at work, which is like a full Haswell. So it could run the 4K monitor, single stream monitor at the high bit rate and work fine because it could clock out enough information. But pretty much the same family of laptops, this one can't. It's frustration because the T540P has a numeric keypad, so that implies it's a large brick. It's why you need a numeric keypad, don't know, but it's a brick. So yeah, that was annoying. So that's why MST monitors probably exist, because Intel do things like that and restrict the clocks. AMD have had actually support for this since Radeon HD 6000 series, which goes back a few years. It's Northern Islands was the family name back then. Like I dug out a Cayman card I think I've had it maybe 3 years, maybe 4 years, could even be a bit longer, and stuck it into my desktop and wrote support for it and plugged 2 4K monitors into it, and they mostly worked. I was like, well, it's not perfect, but for a couple of weeks work, it was like, oh wow, that's really old hardware and it mostly just works. Probably because AMD did a lot of the work on specifying DisplayPort MST. NVIDIA only got on board around GeForce 6000 time. NVD9, I think is the family name, but Kepler, so many specifiers. But yeah, so from GeForce 6000 on, I think pretty much NVIDIA supported. They all have different limitations. Intel can only scan out 3 different things. So no matter how many things you plug in, you can only have 3 different images. Most Radeons can scan out 6. And most NVIDIAs can do 4. So there's different ranges of how much things you can plug in at one time and get away with seeing. Again, it's going to make purchasing decisions painful, but that's why you buy support from Red Hat. Free ad time. So, driver status. I first worked on the i9-15 for this because that was the laptop I had, and that's what Red Hat needed for internally, and so I had to get it working for the docks. We merged it to the kernel for 3.17, I think it was. I've been adding support for the tile stuff, only just got merged. I think it's in DRM Next right now. I don't think it's been merged yet. It's in DRM Next for the next merge window. But I could be wrong. I'm only a DRM maintainer, so I even forget what I'm doing. AMD, I actually have patches sitting on my machine. I've been meaning to send them out, but there's still a couple of small corner cases I'd like to fix, but it mostly works. It mostly works with the monitors. When I've got one of the hubs plugged in and I plug in some crappy old Dell monitors I found under my desk, they don't work very well. At certain resolutions they work and some they don't, so bit of a pain. Nouveau, Ben Skeggs sits next to me. I've given him the hubs. He played around. He's got an implementation that works, but he wants to clean it up as well. And we had I think he's waiting on me to get the Radeon finished so he can just copy what I did. So we'll probably hopefully get that soon. In terms of binary drivers, FGRX and NVIDIA both support the MST stuff. The tiling stuff is actually something that we're all working on. Well, not all, I say all. NVIDIA are interested in us working on it, and nobody knows what FGRX does because we don't talk to those. They don't talk to us. But overall, what does it mean for the rest of the stack? So this kernel support's all sort of there now. Well, the problem was we try to hide these crazy monitors in the kernel. Everyone back, I went to Chicago about 6 months ago, talked to Keith, talked to Linus. Everyone's going, oh, hide this in the kernel, hide this in the kernel. It's crazy. You can't let people see the fact that it's 2 monitors. But I'm going, I know Windows hasn't hidden this. And I know macOS probably hasn't hidden this. And then I went and tried to hide it. And spent probably 2 weeks, 3 weeks hacking away going, I got to hide this. But there was no nice way to hide it. I tried my best. I think I'd tried twice on 2 separate occasions to go from scratch and do it. But there's just so many. When you've got a limited number of hardware resources and you tell a user space policy making thing at the end of the desktop environment that you have that many hardware resources, and then you try to start to hide them after the fact, it gets very confused. It just doesn't understand when I say you can scan out 3 things, and then it tries to scan out 2 things, and then you take all its resources, and it doesn't know what to do. There's a number of other cases like page flipping and stuff is really hard to get right when you're hiding stuff in the kernel. So you tried it, didn't work, moved on, tried to get it fixed. So what did I do? I exposed the tiling property from the kernel through KMS to let user space know this is a tile monitor, here's a property with its positioning and all that information in it. I got Xorg to pass that tiling property through via render so that desktop environments could find it. I hacked up Mutter, because I'm mainly working on GNOME, because that's what Red Hat wanted. I hacked up Mutter, GNOME Control Center, GNOME Desktop Package. There's a few different places. I just wanted to get a proof of concept out, and I hacked it all up, and I was like, oh, this works quite well. You can see the monitor in the control panel. It looks like one monitor. You can see it in Mutter. Things maximized to the right size. So that was a proof of concept. So then I went back to talk to Keith Packard, and we went over it, and I'm currently reviewing what he proposed so we still pass the tiling property through, but then we allow the desktop environment to create like a monitor. So applications don't need to think, oh, how do I create a monitor out of these individual pieces? They just say, there's a rectangle here and there's a rectangle here. Don't need to start worrying them about the fact that there's subdivisions within those at the hardware level. Unfortunately, this means we're going to have to do fixes in like KDE, SDL will probably need fixes. SDL works. Well, I think SDL2 might need some change.
Is the only thing it's broken.
Yeah, no, I think SDL2 will still need, because they do strange things like setting a mode when you start games and things like that need to be fixed. But there's a few things that it's very messy, and I really wasn't happy in the end, but it's the best we can do, and hopefully we'll get it done soon. Myself and Keith are just going to finish off the render stuff soon, and then I'll start getting the desktop environments done, and then I'll start wondering how to get it out to customers and other people. So, future fun, other stuff that's sort of sitting out there that, when I originally went, 5K monitors started just turned up as well. I was like, oh, 4Ks haven't even really gotten out yet. Dell went, we're going to make a 5K. It's like Gillette, add another razor, we're good. So I was like, 5K is better than 4K, or what's that, 6-minute abs? No. So 5120 by 2880. That's a lot of pixels. I haven't gotten one yet. I'm going to ask my Dell friend. They're like $2,500 apparently. So they are on sale, but I don't know if you actually get them, or they just start to go, we'll give it to you when we figure out how to make it. The problem with 5K was there's not enough bandwidth in a single DisplayPort 1.2 cable for a 5K monitor. So even if you've got multi-stream transport, it doesn't matter, because there's not enough total bandwidth to do it. So Dell monitor takes 2 cables, and you have to plug them into 2 separate DisplayPort ports on your machine, and it requires 4 scanouts. So I know maybe it only requires 2 scanouts. I have to check that. It would be really annoying for Intel if it required 4, but it could do. Yeah, I think it's okay to do half. Oh, yes, probably not. Probably not fast enough for Intel to do either a half on its own. So the 5K monitors also made me have to redo a chunk of code, because I hadn't really thought about it enough. All of those tiling properties I was sending out have a group identifier at the start. So if you've got 2 monitors plugged in, these are from the same group and these are from the same group. I originally did that based off the DisplayPort they were plugged into, and then went, oh, that's not going to work out so well, because this can be plugged into all of your DisplayPorts. So I had to go back and read a whole bit of code for that, and I realized the consequences of 5K. The Apple 5K is interesting. I think the iMac that they've made with 5K in it is, it's not cabled for a start, so it's directly connected, and they've put a special display controller in it. So it looks like a very large EDP panel from what I understand. So they've done something very hacky, and it's only on a Radeon, and they're not trying to ship a 5K standalone monitor yet, because they understand it's not going to work very well. Dell, of course, ship it and hope people buy it. So what's coming up to solve that problem is DisplayPort 1.3. DisplayPort 1.3 adds HBR2, which is a 8.1 gigabytes per second protocol. So just make it more faster. So that's interesting. There's nothing with DisplayPort 1.3 in it yet, as far as I know. I haven't seen any hardware shipping with it from any vendor. Possibly AMD will come out with it first, but it'll be another 6 months, I'd say. So yeah, 5K monitors probably won't get too successful before then, but you never know. Another feature that's coming in DisplayPort 1.3 is a thing called FreeSync. If anyone's heard of the NVIDIA G-Sync, I think it's the NVIDIA call. It's basically variable synchronization. So you don't, instead of sending a screen full of data, you can send updates to pieces of the screen to the monitor, and the monitor keeps track of them. So you don't have to send, it's not like you're scanning out the whole screen 60 times a second and giving it to the monitor. You can just send it small blocks and it updates on the monitor side. Again, this is a VESA standard. I think it's part of the DisplayPort 1.3, but maybe a separate standard as well. Unless one of these monitors and one of the cards it supports it falls into my lap, I probably won't work on it, but like usual, things do fall out of the sky when you least expect them. One other thing actually I haven't got on here, but also I just noticed the other day is USB 3.1 has just been sort of announced, and more information has come out about it. And, you know, DisplayPort guys went and put USB over DisplayPort, so the USB guys went, well, we're going to put DisplayPort over USB. Why not? So that's what they did. So you can now get USB 3.1, which is a brand new USB connector that's reversible, and it will run DisplayPort over it. So I'm not really sure what's going to happen there if you start doing, you like USB in your USB and your DisplayPort. It's just crazy. So I'm sure there's other things that will happen in the future that will equally surprise us. I'm hoping the render work to do the monitor support will help us out, because that actually allows for other things that people have wanted to do, like display walls and stuff. We don't really care about those, but it's nice to enable other people to do things when you actually do stuff. But it'll be interesting. I sort of thought I wasn't going to be working much on display technologies this year. I was wrong. So that's my desk at the office. Any questions? The desk, if anyone wants to know. So I think this was a 4K single stream. You can't see my mouse pointer, can you? Yeah, see, can I get it out there? No, can't do it. But the one on the left, well, actually the one on the very left is a really old crappy monitor, but that's a 4K single stream monitor. That one that's at a funny angle because it's on a weird mount is a HDMI, old Dell HDMI monitor. And then you've got the T540p, the T440S, a few Dell laptops sitting, holding them up. That's a 24-inch 4K monitor, that's a 32-inch 4K monitor, and the two that are lit up behind, they're like old monitors, and then that's an old laptop. So that's where I have to sit in the middle of most days. Our office management don't, they do desk audits, and they just leave our little corner alone. So if anyone's any questions, over for the mic.
How long did it take the cable testing guy to test the cables on your desk?
Yeah, so we've got this guy come in and do tag and test every few weeks, or every few months. And he came in about 2 weeks ago, and he walked into our corner and was just like, oh. Probably should have taken it, reserved the day, because that's my side of, that's two desks on my side. And Ben Skeggs sits on the other side, and he's got a desk, and we've got another desk with other stuff, and he's got a desk that's just got NVIDIA cards all over it. So we actually had to help the guy. So we sat there for like an hour or two just pulling cables out and testing them. It was...
So Dave, the multi-stream stuff's only in the new docks. So if you've got, like, I think I'm going to confuse things, because I've got a Haswell that's on an old dock that was worked with originally with a Sandy Bridge Dell, but the dock connectors are the same. So does that mean the dock wouldn't be using the multi-stream because it's too old to have...
Yeah, the dock requires smart. So if it's a Haswell plugged into an old dock, which I thought they'd changed the connector sufficiently.
No.
Maybe some laptop manufacturers left both set of pins.
Dell's Latitude ones go back, I think, 3 generations. So the same dock that worked with, I can't remember, Sandy Bridge, Ivy Bridge, still works with Haswell.
Oh, right, so they probably left all the pieces in there.
Mostly works. I've had the motherboard changed 3 times. But
there's also another area, that just reminded me, there's another thing called of USB docks, which is a separate project, which I also have done work, but it's DisplayLink is the protocol technology company that does that, and they don't tell us how they work, and it's all encrypted, and I've wasted a few months on that lately just because I don't like them. But that's another project where, because a lot of laptops are coming with these USB 3 docks for the cheaper end, and people really want them to work as well.
So we keep hearing these, intriguing talks every year of how you've managed to deal with a whole lot of craziness from a whole lot of different hardware vendors. Well after hardware's been released and available to the public, do you think you'll ever get to the stage where vendors will give you hardware samples ahead of time so you can kind of deal with it maybe a year before release?
Well, this case, like I wasn't even working in this area when it happened, so I was had been working on the virtualization stuff, and I wouldn't have actually wanted someone to give me in advance, because I would have hoped someone else would have done the work if it had been available. I asked a few people, like, are you actually going to do this? And it's like, oh yeah, it's on our list. But it was like, the only reason I actually started this was because Red Hat had the hardware in-house and needed to give it to people in-house. It wasn't even for customers at that point. Like, we have customers now, but at that point it was internal people need this, and supporting the people that work with you is a good way to make money.
So on that topic, we heard from Keith this morning, when Ben finally plays StarCraft, what's going to happen in terms of graphics development?
Nouveau development. Well, Ben replaced Starcraft with a Subaru Impreza WRX, so we're not sure if Ben's going to survive another year or two driving that thing. Hopefully. But yeah, he doesn't play Starcraft, thankfully, yet. I think he played it for a while, and then he realised that driving his car fast was much more important.
Does that mean you're going to keep the graphics then, or are you going to head back to Vert?
Oh, I'm now time slicing between graphics and Vert, as in, I work on this mostly when I feel guilty that my monitor doesn't work properly, and then I get tired, I'll work on Vert, and then I'll work on the reverse engineering project, and then I'll get bored and work on old graphics cards because you need a break.
No more questions?
Thank you for talking. As a show of appreciation, you can give this.
Oh, thank you.